Okay, I want to calculate an expression for the magnetic force between two magnetic dipoles. And in this case, those magnetic dipoles are actually just going to be loops of wire with the current flowing in them. And this is not a trivial problem. So the first problem is that, which I'm going to break this into parts. This is part one. The first problem is that the magnetic field due to a loop of wire, even though it acts like a dipole, we need to calculate that magnetic field everywhere. And I'm going to do that here. I'm going to calculate the magnetic field due to a loop of wire everywhere. The other part of the problem is finding the magnetic force on a loop of wire. Because if we have a constant magnetic field, the net force on a loop of wire is zero. It turns out that each individual piece of wire will have a force, but when you add up all the forces, the net force is zero. So it's a complicated problem. But if we do that, if we find the magnetic force between these two loops of wires, what I'm going to do is calculate the magnetic field due to a loop, and then anywhere in space. And then I can calculate the magnetic force on each piece of this wire, and then find the total force. And then I can change the separation distance. And I can do this all in Python. And I don't know what the answer is. I know that there are a lot of, I tried to Google what's the magnetic force between dipoles, magnetic dipoles, and it's not clear. So I figured, let's just model it. Okay, so what we're going to do is to find the magnetic force and the magnetic field due to this loop of wire. We'll use the Biot and Savart. This is the law of Biot and Savart. And so this says that if I have a short segment of wire, delta L, with a current I, then I can find the magnetic field due to just that short wire. We'll call that delta B. So this mu naught over 4 pi is just a magnetic constant. R is the vector from the piece of wire to the location where you want to find the magnetic field. And then R hat is the direction, the unit vector for that. So we have this cross product thing going on here that makes it much more complicated. Once we do that, I can find the magnetic field at these locations, and I can use this force calculation. The force on a short piece of wire is I times the delta L vector for that wire times B, cross B. That's not times cross. Okay, so let's think about a loop of wire. Because the first thing is I need to break it into finite pieces. So if I have a loop of wire, here, let me draw it like this. It has some radius R and some current I. Let's break it into 8 pieces because I can draw that really easily. So there's 8 segments of a wire in a loop. And so I can have a piece right here, a piece right there, and I can find these pieces, right? So one thing I could do is to say, okay, theta equals 0. That's the location of that piece. Theta equals 0. D theta is going to be 2 pi over n. If I break it into n pieces, I know that the theta step size. And then I can find the location R, let's call this R piece, is going to be the radius of the circle R, capital R, times the vector cosine theta, sine theta, 0. And this would be in the xy plane, but we can change it up. And so then if I change theta by adding theta 0 equals 0, theta 1 equals theta 0 plus d theta, theta 2 equals theta 1 plus d theta. So I can change the theta and find all these pieces. But that's not good enough. That's not nearly good enough. No, it's not good enough. Because I need this delta L vector. So let's just draw some of these delta L vectors. So this would be delta L. This is delta L. I need those, right? And so forth. I need those delta L vectors because that's what I use to calculate the magnetic field, delta L. So how can I do that? Once I know these pieces, RP, for the vector location of the piece, which depends on the center too, because I'm going to move the center. But I'm going to just calculate this for a loop of wire in the xy plane at the origin, and I can find the magnetic field anywhere. That's what I want to do. So if I do that, how do I find this delta L? Well, I'm going to use a little bit of trick. First of all, I know the length of that. I'm going to actually draw this as, let's say, an arrow in Python. I'm going to draw this as an arrow. I'm not even going to draw the points. So the length of that arrow will be delta L magnitude. So I can call that delta L magnitude, or let's say delta L, let's call it that. It's going to be the total length all the way around there, which is 2 pi r, that's the total length, divided by n. So that's going to be the length of each piece. But now what about the angle for each piece? Well, here is the vector r. And actually, I'm going to draw this not right there. I'm going to draw it perpendicular, so it's going to be this way. So these will all be like that, perpendicular to those. And the key is when I have two vectors that are perpendicular, if I want to find that vector, you should think in your mind cross product, right? Because if I take the z-axis, which is this way, and I say z, the unit vector z hat cross r, that will be in the direction of L. So I can say delta L equals this whole thing, 2 pi r over n, times the cross product of z, which is 0, 0, 1, cross rp. Oh, that has to be rp hat, right? Because I don't want the actual magnitude. I want this to be just a direction. That's the magnitude of the vector. And that gives me L, the L vector, the d delta L vector. Then I can find the next one. After I move theta, I can find the next one. Okay, so let's just do that. Let's build a ring with arrows in it. And I've done this before, but I'm going to do it again because it always helps to do things again. And let's just get started. So it's a numerical calculation, so I'm going to need to pick some values. Let's pick r equals 1 centimeter, 0.01 meters. I1, let's say, is 0.2 amps. That's all I need right now. I need this magnetic constant. I'll call it Km equals mu naught over 4 pi, which is 10 to the negative 7th. So I need those values. Okay, so let's switch over to Python. I'm going to be using GlowScript VPython because it's easier to model everything that way. Let me cover up that light because that gets annoying. And switching to the computer. So here we are in GlowScript VPython. Okay, so the first thing I'm going to do is make this a little bit bigger. And then I'm going to put my constants. Km equals 1 times 10 to the negative 7th. R equals 0.01. I1, and that doesn't really matter right now. I'm just putting it in there for temporary, 0.2. Okay, so I also need to create some things like n. I'm going to start with n equals 8, just like I said. Then how many pieces I have. Theta equals 0. D theta equals 2 times pi divided by n. Now, let's just draw these arrows and then I'll add that in there. So the first thing I'm going to do is say this. While theta is less than 2 times pi, right? So I'm going to move all the way around that circle. And so to do that, I could say theta equals theta plus d theta. That's something I definitely don't want to forget. But the first thing I'm going to do is find the vector location of that first point. RP, and I just wrote this down, so I'm just going to type it up. It's going to be r times the vector cosine theta, sine theta, 0. And let's just put a sphere there to make sure that works, and then we can take the sphere away. So I'm just going to put a sphere there. Sphere position equals RP. Radius equals r divided by 10. And then RP will change because theta is going to change. I think this should work. So let's just run this and see if I should get 8 points in a circle. Yeah, there you go. Come on, that's nice. Let's see. B due to loop of current. Save it. Okay. So I don't want to actually draw that. What I want to do is make an arrow. So I'm going to say this. DLT, I'm going to say T for temporary, is going to be equal to just what I said. 2 times pi times r divided by n, right? That's the length of each piece. And then I'm going to say times the cross product of the vector 0, 0, 1 and the unit vector rp, so that's going to be norm rp. So that's just a vector length. Now let's draw that as an arrow, and I'm just going to draw it for now. Arrow position equals rp, axis equals dlt. That's it. And then I'm going to increase theta, so I should have 8 arrows that kind of make a circle. That's pretty nice, right? And it's important to realize those arrows are my DLs. Each one has the same current, but now now it's not perfect, right? Because I'm having this is my location and this is my vector. I should probably have the location in the middle, but I'm not really going to worry about that because if I break this into 64 arrows, which I can easily do, 64, then see you can't even tell, right? It doesn't really matter, and that is pretty awesome. Okay, let's put it at 16. 16 is a good number. That looks pretty good. Okay. So I have my ring broken into these pieces, but I need to kind of reference these pieces more than one time so I can make a function. I want to make a function where I give an observation location and it returns the vector value of the magnetic field. So let's make this. I'm going to say ring 1 equals a list. And what I want to do is to add all those arrows into my list. So I can just go through my list and find the different values of IDL. So I don't want to necessarily have to draw this. I'm going to say this. Ring 1 equals ring 1. The nice thing about lists is you can really add anything in there. And I'm just going to add this arrow. So it's going to look the same, but let me show you down here. I'm going to print ring 1 3 dot axis. I'm just going to print that out just to show you how it works. So it looks the same, but this is the fourth arrow. So it's 1, 2, 3, 4, and this is the direction of that arrow. So I can reference that. That's pretty cool. Let's do something else. Just for fun, I'm going to leave it as color white because I don't really care. I am going to say this though. I equals I1. Now I can do something like this. They all have the same current, that's fine. But now I can say print ring 1, 2 is the third thing, dot I. That's the current for that piece. And it should give me 0.02. Yeah. So now I can reference that. Okay, so we have our ring. Now let's just calculate the magnetic field at some location, just for fun. And let's just see how it works. So I'm going to say RO is my observation location. I'm going to put it on the z-axis because I know I can actually calculate that theoretically too. So it's going to be the vector 0, 0, 0.05, 5 centimeters this way. Now to calculate the magnetic field, what I need to do is to go through each. I guess I should have drawn this. Let's go back to the paper and show you, because I said I'd do that first thing. So paper. So here's the paper view. Not pay-per-view. Okay, the paper view. You see the difference? Okay, so let's say I have my ring right here. And it's broken into little pieces. And I want to find the magnetic field right here. So this is, and I don't even care where the origin is. So this is the vector RO, my observation location. And then I have the vector location, I'll call this RP. That's the location of the piece. I can find this vector, R. R equals RO minus RP. That's the vector location from here to there. And once I know that, and I know the vector delta L, which I do know, then I can calculate delta B is mu naught over 4 pi I delta L cross R hat, that R, divided by, I'll just put it as R squared. And then I can move around the piece and do it for each of those pieces, and then B is just going to be the sum of all the delta B's. So I need to go through that list of pieces in the ring and calculate this. Now, while I have this out, let me go ahead and write down what I want to check. I know that this is true. The magnitude of the magnetic field due to a loop on the axis of the loop, I'm looking it up because I forgot, it's mu naught over 4 pi Li over r square root of r squared plus L squared over 4 over 4. Yep. So I can check my answer on if it's on the axis, only if it's on the axis, and r is the distance from the center. Okay, so let's do this in Python. We are going to use a little trick here. I do like cool Python tricks. Uncool Python tricks are not cool. Okay, so watch this. I can do this super awesome thing in Python. I can say for RPT for temporary in for I want to DLT. I use that already. So let's say DL temp in ring. Print DL temp dot POS. So this is going to go through that list of ring 1, and each element in there it's going to call DL temp, and I can do whatever I want with DL temp. So I'm going to print out the position of each of those pieces in the ring, and we should get a list of, so see, like there it works. Now I can calculate the magnetic field, but before that I'm going to calculate the piece of the magnetic field, so I need the total. So B, I'll call it total, equals vector 0, 0, 0. I'm going to add those pieces to this, so I need to start with the total of 0. Now I can calculate, the first thing I want to calculate is R. So I'm going to say R is going to be RO minus DL temp.POS. That's what I had on the paper. Now I can go ahead and calculate dB. dB equals Km, that's my magnetic constant, times the cross product of IDL. So that's going to be, actually I'm going to put the I over here. Let's put DL temp dot I times the cross product of a DL, which is going to be DL temp dot axis, right? That it is this, the axis is a vector. And then norm R, right? So that's the R hat. Now all of that I need to divide by the magnitude of R squared. And that's it. Now I can just add that. Did I mess that up? Okay. Add that to the total magnetic field. B total equals B total plus dB. And that's it. I don't need to like increase a counter or anything, because it just goes through that list. And it doesn't even matter if it does what order it does. I just need to do it for all those pieces in there. Okay, so let's print that out and see if it works. So I'm going to say print B equals B total in Tesla. Now let's calculate the theoretical. B theory equals, I'm going to use this equation right here, so it's going to be mu naught over 4 pi, which is Km, times L, which L is going to be is that right? L. B loop, no, I wrote it down wrong. B loop is, it's 2i pi r squared, so it's going to be 2 times pi times r squared. Did I get the I? Times I. Divided by z squared, that's the distance along the axis. Yeah, I wrote down the magnetic field due to a wire. So it's going to be z squared plus r squared to the 3/2. So it's going to be divided by z squared, which is going to be equal to 0.05. Let's just call that z. Z squared. I'm going to go up here, say z equals 0.05, and then put this as z. Z squared plus r squared, all of that to the 3/2 power. So 3/2 power to 3/2 power. Raise it to the 3/2. Okay, now let's print that. Print BT for theory. B theory. in Tesla. And I probably made a mistake somewhere, but let's just see what happens. It's not printing all that stuff. Okay. It did not print it. Can't find the variable I. Okay. So let's just change that to I1. So here I got the magnitude of the magnetic field should be in the z direction. So these are really small. Look at this number. You can't see that. 10 to the 20th, negative 23rd, 10 to the negative 23rd, 10 to the 9 times 10 to the 8th, negative 8th, 9 times 10 to the negative 8th. So, I mean, that is really close. And that is only broken into 16 pieces. So I'm pretty happy with the way this works. But now I can put R anywhere. I can put this observation location wherever I want. So let's just change this to Z. I don't know. And I'm going to get something different. But now I get a reasonable value. Now I'm going to do one more thing. I'm going to turn this into a function. I'm going to make this a function where I give it observation location and it returns the magnetic field. Because that's going to be useful. So let's say this. I'm going to put all this in a function. Def B. B loop 1. I want to just call it B. I'm gonna do that. B, I'm gonna give it an observation location RO. And so I don't need this. Okay, now all this stuff I'm going to just indent. And then I should put a note here, returns B for loop. Now, I don't have all my stuff contained in that function. Okay, I don't have the definition of the loop and stuff like that. And that's okay, I can do that. It's probably not the best programming-wise, but it makes the most sense to me. So I start off with a total magnetic field of 0. I go through that ring 1, and I calculate the whole thing. But now I need to just do this, return B total. And so down here, instead of B total, I'm just going to put, let's put R temp equals vector 0, 0, Z, which I had before. And then instead of B total, I'm going to say B R temp. So I'm going to use that function in my print statement, and that it should work. But if it does, let's just run it. Okay, so it still works, right? It gave me the same answer. So now, if I copy, once I make that ring, I can use this function to find the magnetic field anywhere. So the next step is to make a loop of another loop of wire, and then calculate the magnetic field due to this loop at every part of that loop, so I can calculate the force on that loop. But I'm going to do that in the next video, just because I wanted to break these two into different parts. So this is making the magnetic field due to a loop, and now I can use it to find the force on another loop. But that's going to be in the next video, which I will link down below after I finish that video. But right now it's not going to be linked. So there you go. Oh, and I'm going to give you the code for this down below too.